Thank you very much for the kind introduction. And I'll be giving this talk jointly with my PhD student, Boris Ivanovic, who is also attending the workshop. Now, my lab focuses on the design of planning and decision-making algorithms for autonomous robots by leveraging and blending techniques from optimal control and machine learning. A key focus of our research is to design algorithms for interaction-aware decision-making, as needed, for example, in autonomous driving applications. Concretely, consider a highway merging scenario. Despite the fact that in this video, the overall goals of the vehicles are clear to everyone, there is a lot of uncertainty in the outcome of this interaction, which depends on a complex and often quite aggressive negotiation. In general, this video showcases how interactions on the road are really an exercise in negotiation. An autonomous system should be able to perform such negotiations for safe and efficient driving. In other words, autonomous systems should be able to perform interaction-aware decision-making, which refers to the capability of proactively interacting with other agents to infer their intents, while concurrently exploiting this information to take actions that account for agent responses. Our key approach to enable interaction-aware decision-making is model-based, whereby a probabilistic understanding of an interaction dynamics is used as a basis for policy construction. Within a model-based approach, the first step is to design models for intent prediction and trajectory forecasting. In my lab at Stanford, we have developed a general framework to forecast human trajectories, which we call the Trajectron++. This framework is based on a conditional variational autoencoder model that can ingest as conditioning variables for the predictions a vast set of heterogeneous data, from dynamical information, clearly a pedestrian has dynamics different than those of a car, all the way to maps encoding information such as road boundaries and crosswalks, and even human silhouettes to properly predict pedestrian movement. The end result is a Trajectron++, a generative model of a human trajectory distributions that yields state-of-the-art performance on a variety of real-world datasets. Now, this is great, but a prediction module clearly does not operate in isolation. For example, in a standard see, think, act cycle model of an autonomy stack, the uncertainty stemming from the perception module impacts the safe operation of the prediction and decision-making module, the think box here. Accordingly, our current research on the topic of prediction and trajectory forecasting focuses on finding ways to better integrate the prediction module within the autonomy stack, along the three main research dimensions. First, representations of forecasted trajectories that are more efficient to use in downstream decision-making. Second, accounting for uncertainty sources that stem from upstream perception modules. And third, devising metrics that capture upstream and downstream information flows, thereby coupling the design of the different modules. For the remainder of this talk, I will briefly overview our recent work on prediction representations and uncertainty propagation, and then Boris will provide a more detailed discussion on the topic of task-aware metrics. Now, starting with prediction representations, nearly all methods in trajectory forecasting, including Trajectron++, predict tracklets for each agent in a scene. That is an ordered set of waypoints. And this is a natural output structure to provide. However, this representation is not the most efficient to use in a downstream decision-making, as typically planning and control algorithms reason about system dynamics as opposed to tracklets. So the question is, can we devise more efficient representations for planning and control? To address this question, we have recently proposed to represent the trajectory forecasting problem according to a system theoretic formalism. Specifically, the scene is modeled through a linear time-varying system, where the state is a concatenated state of the agents in the scene, and the control is the robot control U of R. U subscript of R. Explicitly, let's consider an example with the 3 agents, with agent 1 being the autonomous car we control, as depicted in the bottom left. Then the state matrix is a 3x3 block matrix, and we have a similar partitioning for the other system matrices. The goal is to learn the Greek components of the system matrices A, B, C. For example, in the case of the state matrix, those components represent the agent-to-agent interactions. The blue components are all known through agent dynamics models and are not learned. Since we're interested in control, the only action present in the dynamics is the robot's control action, U subscript of R. This enables the robot to reason about its effects on other agents in the scene. Given this formalism, the key idea is then to have a trajectron ++ output a mixture of a linear time varying system models, where each component linear time varying system models a high level latent behavior. We've shown that with this more structured representation, performance is minimally impacted, but the integration of a trajectory ++ in a downstream control becomes dramatically easier, as this representation can be plugged trivially within an MPC routine. MPC means in the model predictive control. In fact, model predictive control typically reason about system dynamics in the form of A, B, C matrices, which is exactly what this representation provides. And indeed, learning representations that are more suitable to control is indeed a growing research direction in my lab. Switching to the topic of uncertainty propagation, we have been working on accounting for different uncertainty sources that stem from upstream perception models. Class uncertainty is a case in point. In the image on the left, each object has an associated classification score. Such information, however, is often not considered by trajectory forecasting methods. In a recent work, we have presented a method for trajectory forecasting that explicitly incorporates agents' class probabilities. We have also devised an autonomous driving dataset named PUP that is specifically designed to characterize the impact of a perceptual uncertainty on prediction. And feel free to reach out if you're interested in using this dataset. Complementary to this, we have investigated how to propagate a perceptual state uncertainty throughout trajectory forecasting, with the goal of producing more calibrated outputs. For example, in the figure on the right, we show how neglecting state uncertainty leads to overconfident predictive distributions, in contrast to the case where state uncertainty is accounted for. Detection and tracking provides another major source of uncertainty. In another recent work, we have studied how tracking errors, such as identity switches and fragments, can impact prediction performance via qualitative and quantitative analysis. Motivated by this analysis, we have devised a framework that substantially reduces the impact of tracking errors on prediction performance. The key idea is to simultaneously reason about the multiple sets of tracking results, thereby increasing the likelihood of including accurate tracking results as inputs to prediction. Now, so far we have discussed how to best represent and propagate information across modules. Equally important is to devise metrics that quantify couplings across such modules. And specifically, most trajectory forecasting methods are evaluated in isolation, with metrics that purely focus on the task at hand rather than a relevant downstream use case. In the example on the right, a human driver, depicted in gray, is about to turn right next to an autonomous vehicle, depicted in green. Two predictions, one in solid green and one depicted in with a purple line of the human, are also shown. These two predictions have the same metric accuracy, in particular in terms of a finite displacement error. Although metrically equal, the purple prediction causes a safety-preserving maneuver, the dashed purple line, while the other does not affect the autonomous vehicle's motion plan, the dashed blue line. Task agnosticism can result in predictions that are evaluated as equal, but yield vastly different outcomes and thus driving behaviors, as this example just showed. Thus, we have developed a new task-aware prediction metrics that account for ensuing driving behaviors. Boris will provide next more details about our work on planning-aware metrics. Boris, take it away.
Thanks, Marco. I wanted to start first by saying that, before we dive too much into our method, we really first needed to take a step back and think about what actually do we want from a task-aware metric. And I show, here these two images below. So Marco gave a very nice example from case of prediction. But actually, even in detection, you can have similar asymmetries come up where you have, you might have detections with the exact same, let's say intersection over union, or maybe, some distance-based measure between a bounding box and the ground truth bounding box. And you might also have the similar, asymmetrical output behavior come out from the resulting detections. And so the first core desiderata that we have for a task-aware metric is that it's able to capture these asymmetries in the resulting downstream task. And an important part of doing this is that actually the metric, while it is let's say task aware, it should be method agnostic. And I think what's important about this point is that it's very tempting to, if you are working, let's say, on an autonomy stack, and you already have like a detector, a predictor, and a planning and control module, it's very tempting to just pass the detections and predictions through the planning and control module to see the resulting output, and then to see, how the predictions and detections affect the planning and control module. But the difficulty with this is that, especially in modern systems where you have a lot of development ongoing, you're going to have this moving goalpost problem where the planning and control team will update their code 1 week, and then suddenly your predictor either looks significantly better, hopefully, or significantly worse through kind of no fault of your own. And so it's important to maintain this method agnosticism in order to maintain kind of metric generality, as well as avoid this moving goalposts problem. And then finally, the final 2 points here, being computationally feasible, is important because if you have to run this metric over some large scale data set, you don't want to wait forever, or you don't want to solve you don't want to have to solve like some kind of difficult problem per data set, which then might make scaling this difficult. And then finally, we ideally we want a metric to be interpretable, in so far as that then it allows you to understand, okay, what is actually either causing a performance detriment to the model, or to your to planning and control, or at least just allowing researchers to make decisions based on that. And so Marco, if you go to the next slide, please. We have, so this is the method that we've devised in order to actually develop task-aware metrics. There's 2 core parts, and the first part is to first learn a proxy cost function by which we can kind of well reproduce human motion data that, for example, could be found in a data set. And the important thing here is that I specified that we're working with a cost function. And the reason I say this is because cost functions in planning are basically one level above in terms of like abstraction from an actual planning method, which we want to avoid because that's not method agnostic. And when you deal with planning cost functions, there's many different ways to minimize cost functions. And you can have many different solutions from them. But broadly, planning cost functions capture kind of your objective and what you're trying to do in the problem. And in particular, why we want to learn like a proxy cost function rather than using like a specific planner's cost function is, again, to maintain this method generality across maybe different planning modules or different kind of high-level goals that like a robot might have. And so what we're doing in this work is that we first take human motion data and a set of cost function terms, and then we perform inverse optimal control with these in order to obtain a weighting that actually then combines these into one cost function. And then on the next slide, we'll see that once we have this cost function, what we can do is we can compute the gradients of the cost function with respect to detections and predictions. And that's actually what this, so I have, some bolded terms here, but really all these are is just, so S of T is just the current state of all the agents in the system, including the robot. Then we have the control of the robot, because that's, we know at least what the robot, this is kind of the action that we, in planning at least, we're trying to decide. And then we have this S hat is kind of the estimated states of other agents in the current time frame. So for example, from detection, and then also in future time steps, which for example would come from prediction. And so what we can do is when we compute this gradient of the cost function, and in particular the magnitude of the gradient, we obtain a notion of planning sensitivity. And really what that means is we're basically just measuring how sensitive is the ego robot's planning, or at least this proxy cost function, is to changes in the detections and forecasted trajectories of other agents. And the idea here is to use this planning sensitivity to inject planning awareness into existing metrics. So Marco, could you please give us the next slide? So let's actually, check how this performs, because we have quite a few moving parts here. I mean, we have to learn this cost function, we have to then take the gradient, and then we have to see actually how we can even use this in metrics. And so what we first do is we take some real human motion data from new scenes, and also a set of cost function terms such as lane deviation, control effort, collision avoidance, distance to goal, etc. And we run them through an inverse optimal control algorithm to obtain a cost function, which is an additive combination of these terms with the learned weights. And the first thing that we want to do is we want to say, okay, actually, how reasonable is this cost function that we learned? I mean, if it is really just a linear function, can it actually model the motion that we're looking for? And so what we can do is we can actually re-optimize. We can, or I shouldn't say re-optimize, we can optimize this cost function to see what the resulting behaviors are. And on the next slide, we can see that actually these reproduced behaviors are very accurate, very close to the original motion. And what we can see here is basically we minimized the cost function in 2 steps. So you can see the result of the first step in orange. This is the result of a convex optimization on the terms in the cost that are, well, convex. So for example, you might have a quadratic, many different quadratic terms for lane deviation or reaching the goal. But where you have this interesting non-convexities is in collision avoidance. And this is why then, after our convex optimization step, we use this orange solution as an initial guess to a non-convex solver, which then minimizes the full non-convex cost function and yields the resulting output in green, which we can see very closely matches the blue ground truth ego vehicle trajectory in a variety of different scenarios. So, okay, great. We can see that we can optimize and obtain motion. But now let's actually see what this notion of planning sensitivity is like. And so, okay, once we take this cost function and we compute the gradients, we can see that when we compute the gradients, so on the left here, I have an example of the sensitivity of the ego robot's planning to certain detections. So we can see basically the ground truth bounding boxes are in blue, and then the detections are in red, but basically they can scale in color from red to yellow or gold, where basically based on the magnitude of the planning sensitivity. And so in particular, we can see that, when there's a purple, like when there's a red on top of blue, that just means that it's like a not planning sensitive detection on on a correct detection that's on the ground truth agent. And what we can see here, in at least in the detection case, is that these false positives. So the ego vehicle is in orange here. So these false positives, like an errant, detection of a vehicle next to the ego vehicle, or like a bike or something like that. Like for example, on the right image, these render as highly sensitive detections. And the same is also said for these parked vehicles. Well, parked vehicles, but the problem is that in a single frame, if you're saying that they're facing the ego vehicle, who knows if they're parked or not? And this is where maybe a little bit of semantic information actually might help. And then in prediction, we actually also see some very interesting behaviors in a variety of scenarios where, so here again, in keeping a similar color scheme, we basically have all the other agents are colored in blue, scaling up to red based on their planning sensitivity. And in particular, we can see some interesting cases. So for example, on the top right, where we have pedestrians that are about to turn right on their sidewalk in order to cross the road, we can see that, our method for indicating planning sensitivities is actually highlighted that the two pedestrians specifically that are turning to the right are going, to influence the ego agent's planning. And in reality, they actually do, because once the pedestrians do move there, the ego vehicle actually stops in order to let them cross. And so this is nice that actually we can obtain the fact that, the ego vehicle's planning is sensitive to these agents from even just, such a simple cost function that we learned here. So, okay, let's, once we have these planning sensitivities and we can point out how they, how different agents affect the ego vehicle's planning, let's now actually bring this interesting value into metrics, which was actually the whole point of this project, right? Is to inject this planning awareness into metrics. And in the paper, we kind of thought of two different ways of doing this. One is, internally, is by actually changing internal metric thresholds based on planning sensitivity. So I gave the example here of like computing a precision recall curve. And in particular, something that happens inside a precision recall curve is you have to denote what is a true positive, was it a false positive, et cetera, et cetera. And usually there is intersection over union metrics or even distance-based metrics that are internally used in order to define this this threshold and to define what's a true positive and false positive. And so what we can do is we can actually scale this threshold, in effect rendering, it forces the model to be more accurate on more sensitive agents. And so we can see, we can see what the scaling does. And of course, it's going to reduce performance if the model makes mistakes that are on agents that are highly sensitive, or it causes, the mistakes that are highly sensitive in detection to the ego vehicle's planning. And then we can also do something externally, where basically we can compute existing metrics, but we can striate them based on the ego robot's planning sensitivity to a specific predicted agent. So I give an example here of an evaluation actually of the Directron++ model on the nuisance data set again, but I'm particularly, focusing on vehicles from that data set and pedestrians from the nuisance data set. And we can see, for example, across, both displacement error type metrics and something like negative log likelihood, we can actually point out that, okay, for vehicles, actually Directron++ achieves its best performance, its lowest error on highly sensitive agents, which is good. This is, what we want to see. And then it achieves its higher error on, less planning sensitive agents. And then, the same can be said for pedestrians, or at least the similar can be said, where its performance is good on, funnily enough, both low and highly sensitive planning agents, agents with planning sensitivity, but less so for moderate or kind of agents that are a little bit more effectual in planning. So, okay, so stepping back a bit. So once we have, these metrics, this is all well and fine. And this is actually very encouraging, at least for future research, because once you have this ability to obtain planning sensitivity, there's actually quite a few different things you can do with this. So one example is that actually, because this cost function is fully differentiable. I mean, there's no fancy terms in here that render it difficult to calculate gradients for. Actually, something interesting to see would be what happens if you try to inject this planning awareness at training time. What differences in training behavior would you see? What differences in the output behaviors would you see? So I think that's one interesting direction. And then another is to actually understand the coupling of autonomy stack modules. So, for example, if you see that, detections are very frequently highly affecting the ego vehicle's planning, then that's telling you that, the detection module, even though it's more, so to speak, more upstream in the autonomy stack, it actually has, a significant effect on planning, even though, it might have other downstream consumers such as prediction. And then finally, with scenario generation, what you can do is once you have, this measure of the ego vehicle's sensitivity to other agents, you can then, for example, inject adversarial disturbances into existing scenarios by saying, okay, in this specific scenario, if we wanted to change an agent's behavior in order to affect the ego vehicle's planning, well, this method is able to tell you, okay, well, this agent would yield the maximum difference to the ego vehicle's planning, and it would even tell you, in what way, because if you take a gradient step, you're taking a gradient step that is directly making the ego vehicle's planning costs worse. And so you could, for example, directly affect the ego vehicle's planning in the worst way, so to speak. So wrapping up, we've talked a lot about, here, Marco's touched on this mostly, about generative models as being, the current used paradigm in trajectory forecasting. And I think this is really reflected throughout the industry, where they're really now becoming the state-of-the-art tool. And we have a nice kind of tutorial style paper in IEEE RAL with a colleague of mine from the lab, Karen, where we actually provide an overview of both generative models, but specifically taking a look at how conditional variational autoencoders have been used in order to inject multimodality and actually handle the kinds of interesting uncertainties that we care about in trajectory prediction. We also have a blog post here that I wrote sometime last year that also gives a bit more information on both the field, but also Trajectron++. But having said all that, even though they are state-of-the-art methods, it can be quite challenging to integrate them within autonomy stacks. And towards this end, this is actually what we touched upon in this talk, where in our lab at Stanford, and also at NVIDIA, we're dealing with, we're reasoning about the prediction representations that are cognizant of downstream control applications. We are reasoning about how to propagate perception uncertainty through trajectory prediction to planning in order to make more informed decisions. And then finally, we're studying how to evaluate autonomy stack modules in a task-aware fashion, so that we're able to enable researchers to still work on modules independently if they want, but have a sense of what their downstream performance might be like. So with that, I want to thank you all for your attention and open it up to questions, if there are any.
Thank you.
Thank you very much, Boris and Marco. Very nice presentation. Any question from the audience? Okay, so very nice and clear evolution of the methods on for trajectory forecasting you guys presented here, and I think I do really appreciate the storyline. One of the questions that I always have when it comes to trajectory forecasting, and you touched upon the uncertainty in prediction and future predictions, and also several recent methods that were developed by you and others are trying to capture this uncertainty, somehow create some sort of multimodal future predictions. One of the problems that I have often reading these papers is the evaluation part, how to evaluate this uncertainty, the multimodal aspect of it, because it's always in the data we only have one future only, and then when we want to evaluate, it becomes very tricky, because you can very easily trick the system to get very good numbers, like by sampling a lot and then evaluating based on the best. What is your solution? What is your insightful thoughts about this in general? I think this is something that the field needs to find a solution to, but I would really love to hear from you, Marco and Boris.
That's a great question. Actually, it was a key contribution of Boris' PhD. So I'll let Boris go first.
I mean, I think, yeah, I'm glad you say this, because I purposely never try and use that best of n metric or whatever. And then of course, reviewers always ask me and I'm forced to do it. But yes, I fully agree with you. I don't think this is the way. I think when I first started, especially when I was doing a lot of just pure trajectory forecasting work, I was like, okay, negative log likelihood is obviously the best, right? It's like, it is clearly the method that captures as much uncertainty as possible. But okay, I understand that, for example, GAN-based methods and other based methods, if you just sample, it's hard to do this. And so, something that we tried at first was, okay, maybe that's okay. Even if you can just sample, let's sample thousands of times, fit a distribution to it, and then you can still try and do some type of log likelihood. But okay, let's even step above, this, because okay, this is, as you said, we only have one feature. This is a purely accuracy-based metric. We still might be missing something. And this is where I think this task awareness comes into evaluation. And this is where I think these types of metrics become important. And even before talking about anything about our work, something that I like that I've seen in the community is basically metrics that are like evaluating, for example, rather than just evaluating the accuracy, they'll evaluate like road boundary collisions between vehicles. They evaluate almost like the plausibility of, for example, if you're forecasting many agents in a scene, you can evaluate like how close do agents get to each other, how much does the, let's say, statistics of the forecasted or generated scene match maybe like real world statistics or something like this. So there are ways of like, for example, doing a little bit of like marginal matching, like in order to see how realistic is what you generate. And maybe how like semantically realistic, like, does it stay within lane? Does it change lanes, etc. So I know, for example, Raquel Tasso's group has done this kind of work, or at least has done this kind of evaluation, which I think is I think definitely a great step outside of pure accuracy. And then I think, I'm always happy to also plug our own, I think this task aware metrics that we're developing, where we kind of have this like consideration of like the planning aspect of the planning cost that the ego vehicle is evaluating and how other agents are affecting it. This is also where you can get a sense of like, if your predictions are bad and they affect your ego vehicle, that is, at least from an autonomous vehicle perspective, that's got to be fixed immediately. If you make a mistake 100 meters down, almost no one cares. But if you make a mistake, which affects the ego vehicle's planning, this has to be dealt with immediately. So I think it's where we bring task awareness in. I think this is how we address this evaluation problem.
Yeah, so to wrap up, I think your point is great. You're right. Standard metrics might be misleading because people might tweak them to make their method shine. And that's why recently we're putting a lot of emphasis on devising new metrics that in a more nuanced fashion assess the value of forecasted trajectories. We took the approach of task-aware metrics because from the point of view of autonomous vehicles, I think it makes sense to really have metrics focus on the outcome of your forecasted trajectories. But more broadly, one of the points we wanted to make with this presentation is the need, indeed, for more nuanced metrics to assess forecasted trajectories in order to move this field forward.
Yeah, I think I just would like to add to that comment. I think it was CVPR 2019. I think I had a discussion with Boris regarding the metric of how they are not reflective. Not okay, definitely on the trajectory forecasting, and with respect with the research community. Unfortunately, when something becomes like a popular, it's hard to change the mindset of the community, and I tried with different things, and I just find out is harder when there is one first paper do a mistake and the other couple of paper really follow it. The hardest to convince the community to like there is a need for that. And I believe what Ehsan mentioned is addition, means we have a couple of mistakes in the trajectory forecasting evaluation, which exists now. It's the way we evaluate the generative model is we are just trying to find the best sample, which is not really, we have to really find the mode of that distribution, then compare it with ground truth first, even if we want to say. And also there is not one truth. And that's definitely, I think, valid point. And thanks for your contribution for that. I hope the community appreciate that one as well.
Yeah, so at the minimum, I hope that the future challenges, I mean, one of the reasons why ADE and FDE, for example, become so popular is that there have been a lot of challenges where people really try to optimize for those metrics. So I hope that in the future, future challenges will actually augment. ADE, FDE are important, but they will augment those metrics with more nuanced metrics, task awareness or something else, so that we can have a more balanced view of the performance of a given method.
Yeah, definitely. We need also this to be taken care about this sum of benchmark, which is human trajectory forecasting, is beyond the global motion, but that's same here. Sorry, Ehsan, I have very quick. Now it's not question, it's just comment about the one of the work is that it's the work was accounting for tracking uncertainty. Just I really worked for quite a while on multi-target tracking, and then forecasting problem from my perspective is not something sequential to the tracking. Means we are again, means if we could really do tracking in real time, we are assuming we have the model which end-to-end train to do tracking. Forecasting is predicting beyond time t. And if we could really predict, we can improve the tracking. Means these two problems is joined. The errors, it comes into the when we try to solve the problem in sequentially. Means then we have to deal with the what's the problem with the ID switch? We have fragmentation. We have if we properly model it from sensor to tracks at time t and beyond, then actually beyond can be used to refilter exactly the next time frame and next time frame. I'm trying to explain it. It's that we don't need to really process the data due to tracking, then do forecasting. And that's my comment only.
I think it's a great point, and indeed where we are going toward, actually. That said, the practice in the industry arguably is to do that separately, so that there is still value to find methods that account for the errors in tracking in order to fix the current situation, at least on the industry side. But I agree with you that the next step is really to reason more, still in a modular fashion, but with the end-to-end training approach.